Still more students coming. Oh, that's not that. All right, so everyone now is working on big data, so I'm also working on big data. I'm not just claiming I can prove it. Okay, so the proof is the first slide I used for my PhD defense in 2006. So now I can claim that I've been working on big data for more than 10 years, except that we didn't call it big data. The term was not invented yet. So in particular, I work on algorithms for big data, including external memory algorithms, data streaming algorithms, parallel distributed algorithms. And recently, our focus is on sublinear time algorithms. In particular, the assumption is that you don't now have the time to look at even once at all the data you have. So you have to use random sampling and other techniques to deal with our problem. And I work on both the theory and as well as the practical side of these problems. So to make things more concrete, let's take random sampling as a concrete example. Of course, in the standard model, random sampling is trivial. You can access all your data. However, the problem becomes more challenging when you have your data sitting on disks, or when data comes in as a stream, or in the case where you have many streams in a distributed fashion. Okay. So in particular, our current focus is on this we call query sampling problem. Namely, here the data is not given to you. The data is given by the query implicitly. So namely, we want to get a sample from the query results without actually evaluating the query. Okay, so here is a screenshot from one of our system demonstrations this year. So here suppose we have a lot of points in the map, and when the user looks at a certain region in your map, he wants to know a rough idea of how the points are distributed. But there can be millions or even billions of points in the range, so retrieving them, all of them, might be very time-consuming. However, in this case, a random sample from the query results might be as good as all the results themselves, okay, and all of them. And another problem that we have been working on now is the problem on joins. And as many of you might know, join queries are arguably the most important and essential issue in any relation database. And this query is actually taken from the TPC-H benchmark. It involves 6 tables and 10 gigabytes of data. And even on Oracle, it takes more than an hour to process this query. On the other hand, our algorithm can finish it in less than 10 seconds. Of course, this is not entirely true. Otherwise, it would kick Oracle out of business. So there's a small footnote. And the common wisdom always says that the footnote is always more important than the main text. So let's look at it. The footnote says it returns an answer with 1% error. So it's not an accurate answer. But most likely, 1% is not a big deal. So as long as a small error can be tolerated, our algorithm can return the results much, much more efficiently. And we are currently working on implementing the algorithm in an open source database to make it really useful. All right, so I don't have time to tell you how to do it, but I can tell you how to not do it. So if you just take a sample from each table, then the results will be almost empty. And the reason is that for a join query, the tuples from 2 tables have to match. And if you just take a random sample from each table, the probability can be exceedingly low. So the problem is not as simple as one might have thought. All right. So in general, my work, the main approach in dealing with big data is to scale up or scale out computation. And there are many great ideas in this area. However, my approach is the other direction, that is to make data small, namely scaling down data. And random sampling is, of course, one of the main approaches, but that's not the only one. We have many other techniques like sketching or data histogramming, and things like that. It is to know that this approach is complementary to the first approach, so we can actually use both for dealing with a certain given problem. Okay, and and that's all I have. And I can still take one more student, so if you are interested in my research, you can talk to me afterward.
It is. Okay, so in the last 10 years, my student and I have been working on something called literature models. And we were the first one to start those models, and we have applied this to a number of domains. To explain what they are, let me start with some quick questions about clustering. So here I have some pictures. How do I class those pictures? And obviously, I should just divide in two groups in terms of style of the pictures. Second question, now how do I class those pictures? If you think for a while, you will know that there are actually two ways to get to this. One is to in terms of style, another one in terms of the object in the picture. So this actually, you have two ways to cluster the same data. This is a concept of multi-dimensional clustering. So in general, complex data usually have multiple facets, can be meaningfully partitioned in multiple ways. But the trick is, how do you find those multiple ways to partition data? To answer the question, let's go back to just one partition. To get one partition of data, you can use finite mixture models. If you data is continuous, you can use Gaussian mixture model. If your data is discrete, you can use latent class model. But the point here is you have only one latent variable in your model. So now we want multiple partition. So naturally we need models with multiple latent variables. Okay, so latent tree models are just one such class of models. So we have example. So here it says that the grades the high school student get in math and science depends on his analytical skill, and the grades in English and history depends on his literacy skill, and those two scale variables are correlated. So here you have two latent variables. In general, to learn literature model, you basically start with the data on observed variable, but you have to determine everything behind this box. And then, so that includes the number of latent variables you want, and then the number of states for each latent variable, the connections, and the probability parameters. So it's actually a very difficult problem, but it can actually doable. So in the last few years, we have developed several generations of algorithms. Now we can actually handle pretty big data, not huge data, but pretty big data. So here's the result we got from 2000 NIPS papers. Those words in the RN, that's the observed variables. In the nodes in the inner range are the latent variables. We have lots of them. Each latent variable gives us one partition of the document, and the clusters in the partition can be interpreted as topics. So here's the sum of topics. The first one, you can see, obviously, is about probability theory, and it's consists of 22% of documents, and you have several subtopics about several aspects of a probabilistics method, like the EM algorithm, mixer model, generative model, variance, and noise. Second topic is about image analysis. Also have interesting subtopics. And here's the model we got from 300,000 New York Times data. Looks beautiful picture, but structure meaningful and topic also meaningful. But the key motivation for me to develop literature model is that I want to use them to solve some fundamental problems in traditional Chinese medicine, that is TCM. So TCM theory was written in ancient times. They were based on clinic practice. Clinic practice basically is just data. It's a lot of data. So in ancient times, people process those data, use their brain. They come up with TCM theory. So in the past few years, we have analyzed about 20 data sets from different domains, used literature models, and our results actually match the TCM theory pretty well. So that's actually quite cool. We provide some validation to this ancient theory. We also try to solve some practical problems with TCM. So here, TCM usually is used to treat chronic disease such as diabetes, hypertension, and depression. So here, the first step is to divide the patient into classes, subclasses, which are called syndrome types. And the different subclasses are treated in different ways. So now the classification is done by expert. The problem is the different expert can tell different things. So that's a big problem, right? That's actually undermine the confidence of people on Chinese medicine. So basically, we in the last few years, we have used literature models. We have developed a evidence-based approach to solve this problem. And we believe this should have some big impact to the TCM field. And obviously, I should, we actually have 40 seconds. So one particular disease we apply this to is something called vascular mild cognitive impairment. This is like old people, the word dementia, right? So before dementia, you have this VMCI. And if you treat this properly, then you can defer the dementia or actually avoid it. And TCM actually have strengths in this kind of area. But then, my collaborator from Beijing Dongfang Hospital say, how do we do a classification? So they come to me, we work out some nice classification results. And that's all I have. Thank you.
Okay, good afternoon, and I'd like to take this opportunity to talk about my research on multimodal interactions with and through social digital media. So the development of computing technology make it possible to represent information and data in with rich format, and also it ensures the constant connectiveness among human users. So my research focuses on 3 areas. The first is digital media that are designed to enhance social communication. The second is social media empowered by rich digital content. And the third is interactions and experienced with integrated social digital media. So my first research area concerns with how to represent information and data in a way that it's easier for users to perceive and interpret, especially given different context, different needs, and different capabilities and constraints of the users. More specifically, I've looked into how to represent information and data in terms of text and speech, images, animations, videos, and sounds. For example, we have been developing an ontology of everyday concept based on existing linguistic resources, and then we design algorithms that can automatically assign images, icons, sounds, videos available on the internet to those concepts in the ontology. So on top of this ontology, we were able to design different communication support systems, both online and on mobile devices. In addition, we can transform those digital representations into physical objects so that the users can leverage additional sensory channels. An example is our food messaging system that can 3D printed social messages sent over the internet so that the users can not only read the message but also smell and taste them. So we conduct large-scale usability field study, which shows that incorporating additional sensory channels did help convey subtle information such as emotion. It also strengthened interpersonal relationships. My second research area concerns with how the use of digital media affect users' behavior in social media. For example, we have looked into the use of game elements in online volunteer communities and in online learning communities. We also look into the use of video conferencing in social commerce and in crowdsourcing platforms. One of my ongoing projects about Danmu, it's an emerging paradigm that overlays scrolling comments on top of streaming videos. And we're interested in Danmu users' unique linguistic and social practices and how we can leverage this new social media to do like crowdsourcing, collective creativity, etc. And my third research area concerns with scenarios where the integrated social digital media are represented as social actors themselves, for example, in the form of a virtual avatar or as a physical robot. So we have been designing how to communicate information through linguistic as well as non-linguistic channels such as facial expressions, gaze gestures, and biosignals. So to enhance the collaborations between human users and the virtual avatar or robot. So I am taking students, and if you are interested in any of these topics or have any questions, please feel free to contact me. Okay.
1, 2, 3. 1, 2, 3. Can you hear me at the back? So I've got more time. They both have time left. I can use them all. Just introduce me first. My name is Brian Mack. My research area is automatic speech recognition. So today I'm going to give you a 5-minute crash course on speech recognition. I'm not going to talk about any very detail about the research. So I guess you're all from science. In high school, in your chemistry, probably you know that in this world, you can divide. If you want to find the basic elements in this world, you find that this world consists of about 115 different kinds of elements. They are the basic units. So if you want to talk about water, what's water? 2 atoms of hydrogen and 1 atom of oxygen. So everything is composed of these basic elements. Similar thing happens in speech. If you talk about all the sound, no matter what is the speech, what kind of language in the world, the basic component of each language is some sound. And this is an example of English in using the IPA symbols. And this is the list of symbols, basic sounds in English we call phonemes. There's a web link here. If you go to this link, say if you don't know how to speak this sound.
Oh, or, ear.
That's what I mean by the sound. So these are basic sounds of the language. In English, usually you can, depends on how detailed you're looking into, we are talking about 40 to 60 basic phonemes. And the good thing is every word is just a concatenation or a sequence of phonemes. So unlike the molecules in your H2O, H2O is kind of 3-dimensional. With speech, it's a little bit better. It's 2-dimensional, and it's sequential. And if you look into what's an utterance, spoken utterance, a spoken utterance is just a sequence of words. And what's words? Words are just a sequence of phonemes. So at the end, an utterance, any utterance is just a sequence of phonemes. So what it means is that to do speech recognition, basically, you are going to decipher what are the list, what are the sequence of phonemes in that utterance. Of course, there are some restrictions because not all combination, or not all sequence of any combination of phonemes are possible in your language. And to model sequential data, one of the good tool is the hidden Markov model. To computer science people, this is just a finite state machine. But then we put 2 stochastic process onto this finite state machine, meaning that the transition from state 1 to state 2, from state 2 to state 3, all these are governed by probability. And then out of each state, we call HMM state, then you emit some acoustic, in our case, acoustic observation, acoustic vectors. And in speech, it turns out that it's better to convert your speech in time domain into time domain with the energy into something called frequency domain or spectral domain. And then you've got a nice picture. And this is a picture of
Ryan Mack.
Me. And it turns out that if you turn into the spectral domain, things becomes more invariant than if you look at the things in time domain. And used to be, in the past, people model each HMM state distribution using the GMM, Gaussian mixture model. These days, with deep learning, we start to do using deep neural network to model the distribution each MM state. So in reality, that's what the common usage. Use even all the big labs. Input units, roughly about 1,000, and you use about 5 to 7 hidden layers. And each hidden layer has about 2,000 units. And in terms of output units, it's about 5 to 10K. In one paper from Microsoft in 2011, they are very proud of them saying that, oh, we are using 10K output units. It's the most, no one has ever used so many hidden units, output units. And this year, we have a paper showing that we can do with 60K. In the same conference, IBM is publishing with something like 32K output units. And that means you got a total number of ways we talk about in terms of almost 10% of a billion. So to gauge the progress in our area, so here is one common database we have been using.
Mom, see what I mean? Hi. It's not like you say that.
So this conversation are taken from the switchboard in a telephone company.
You can't get them, you just hang up and then you try the number all the time.
So you can see 2 people
So I never
talking.
got to this point because I only got
kind
Elena
of
Joe
the
that
speech we are
time.
talking
Oh.
about. So in this database, when it was collected in 1982, when it first came out, the word error rate is 70%. It's not a typo, it's 70%. That's the time when I first entered my PhD. I thought it's an accuracy. It turns out it's an error rate. And after 10 years, it got down to 20. And when we used DNN, now it got down to the most recent one from IBM is 8%. And human can get to 4%. So this is my final slide. And for those students who don't believe in people, that is from the newsletter from our IS professor. Thank you. I'm going to talk about the networking system research conducted in my group. And okay, this is our system platform we built in the last 3 years since I joined the department. Now we still keep working on this platform. And let me. Some of you may be interested in knowing more about these platforms, the different components. Actually, if you can see at the top, actually are the switchers. Okay, at the bottom are the commodity rack servers. Okay, and if you see from the left, actually here we have over 10 1G electrical packet switch, each of which has 48 1G port and 4 10G ports, okay? And in the middle, we have a 10G electrical packet switch. We have 3 of them, and actually this one is more expensive than this one. And each of these switch has 48 port 10G Ethernet port and 4 40G port, okay? On the right, actually, are the optical circuit switch. We have 5 of them, and each of which has 16 optical ports. And it's worthwhile to mention that this optical circuit switch are designed and implemented by ourselves, which means that it is globally unique. You cannot buy it anywhere unless we release it. And all these different components are connected together. They can form 3 very meaningful system architectures, which are pure electrical. If we connect all these switches to the electrical packet switch, okay, it can be pure optical. If we configure all these servers to the optical circuit switch, and it can also form hybrid electrical optical architecture. And the experience I gained in the last 3 years is that building real systems like this, though very tough in the middle, and you will have a lot of fun. So please do email me if you want to play with it. I would say it's very, really a fantastic testbed to translate your ideas into practice. Okay, on top of this real system platform, our research forms a systematical way in a bottom-up manner, all the way from the infrastructure level, infrastructure design, to the computing platforms for applications. And at the infrastructure level, we have designed OSA, which is the first ever all-optical data center architecture. And now we're working on Big Switch, which actually is we try to design a massive port data center switch that can deliver very high throughput, very high bandwidth to big data applications. And at the nuclear, we work on both intra-data center routing, explicit routing control, and inter-data and big data transfers. And on the transport layer, our goal is to design ultra-low latency data center transport, which include both flow level scheduling and co-flow level scheduling, taking into account application semantics. And regarding the computing platforms for big data applications, actually we try to combine the effort or combine the efficient network system technologies we developed above, okay, to enable very large-scale distributed computing for big data analytics and machine learning algorithms. Actually, we are working. We have a concrete project on this. We are working on. So our ultimate goal is to design or to find simple, practical, ready implementable solutions for to speed up real applications. Actually, I have a backup slides to illustrate what is a very simple and practical research we conduct. But unfortunately, I have no time to talk about it. I will, if you are interested, I can talk it to you offline. Thank you.
All right, good afternoon. My name is Charles Zhang, and I work on programs. So I'm going to talk about writing the good programs is very difficult, and there's a lot of research interesting can be done to catch these mistakes. So I want to talk about buffer overflow. Right? So if you've never heard of it before, it's one of the oldest security problems out there. So what buffer overflow is that we're copying data in our programs, and we're copying more than we should. Right? We're copying beyond the legal limits. So if these memories on the stack, we can hijack the running memory by replacing the return address of the functions. If it's on the heap, we can steal information that we shouldn't be seeing. All right. So it gets as early as 1988. So Morris worm is the first buffer overflow bug, and I'm going to talk more about its recent incident, which is the heartbleed. So heartbleed bug is the most glamorous security bug in recent history. It's a serious security flaw in OpenSSL. It is the most widely used security library for C for secure network communication, such as HTTPS. This bug is hatched in December 2011 and discovered in April last year. More than half million websites are affected, including our own, and there are more than 24 of network routers are also affected, and tens of thousands of units needs to be patched. Right? So it's a big deal. What is the beast? So the beast is this function call inside this particular file, TLS1 process heartbeat. So it tries to copy some buffer from PL to BP by the payload. Payload is the length. So the problem is that the attacker can control the target memory and the length of the buffer, and the payload can be very small, but the length can be arbitrarily large. In this case, 64 kilobytes. So you can see that you can copy arbitrary messages into the outgoing buffer. So the problem is that this is a very hard to find bug. OpenSSL is close to 500,000 lines of code, over 3,500 functions. And this memory copy, has 600 places in this program. All right, so for the heartbleed bug itself, it spans 7 files over 13,000 lines in 44 functions. Just think about the effort of inspection. So Linus says, given enough eyeballs, all bugs are shallow. And I personally don't believe that. And our research is trying to use software AI to replace the eyeballs. And our objective is to produce a very few reports through static program analysis. So you can think of as a compiler that is very smart. You first try to look through all these mem copies. Of course, that's not enough. And we have to look at other constraints, such as the length have to come from the network, and unchecked, the source has actually come from the network, and the source data size is much smaller than the length. So we can almost certain that there's going to be a problem. All right. Actually solving this problem is quite challenging. We need to do a lot of different techniques all together to solve this problem. We need to do a context-sensitive analysis to walk up and down the call stack. We need to do path-sensitive data flow to understand how data is passed around. We need to do pointer analysis to understand how data is accessed through the heap. And we need to do abstract interpretation because we have to understand the length of one data size is much smaller than the other. And we need to do proposition satisfiability to understand the predicates in the program. So all these is either exponential or undecidable or NP complete. So the problem itself is quite challenging. And we're actually attacking this problem by using some symbolic pointer analysis. We use Serum Prover to understand the program path logic. And we have summary-based data indexing to allow us to scale to very large programs such as SSL. Right? So that's all I want to say about my next research direction, not the past. Thank you.
Okay, so is the mic working? So I'm going to talk about some research that I'm working on with my student. So in my, for my, most of my academic life, I spend most of my academic life working on, communication and networking in extreme environments. So extreme in the case of, either extreme remote, extreme, rural, or extreme, high latency. For example, the communication between the Earth and the Mars. So, you can couple of minutes, and also, extremely crowded. So that, tens or hundreds, tens of thousands of people in the very small areas. So that, require different kind of networking protocols. So, we have I have been to many places in the world, and we try to bring connectivity to the people there. So this one is, in Laponia in Sweden, very north of Sweden. So there's people doing reindeer herding there. There's a community. So we've been there, a couple of years ago, and help them to bring some connectivity to the internet. And here is Brazil in Amazon jungle. So people live in the jungle, and they don't have internet activity, but they have school. So small school kids, study. So we went there and also help them to set up some connectivity so they can study better. So this is Swiss Alps extreme cold, and maybe networking or sensors not working properly there. So we also went there. We run some tests. We build some system tests and in the mountains. So did you know how to pronounce the name? Let me know. So it's in Iceland, volcanoes. And I'm on the top here. So we also been there, and also some experiments, and also connectivity tests, and set up a system to bring the sensor, because we sensor deploys to monitor those activities, right? But you need some way to get the sensor data into the city, so people can working on this. Then this is another place in Ecuador. So as the place that Darwin discovered is origin of life. So extremely wide diversity of animals. And so today we also bring this connectivity to UST. So this is a work with a startup company in US, and this was reported by MIT Technology Review. So they built the first system to enable a commercial system for communication using device to device. So only device. So we don't need infrastructures. So we're going to. So this is going to the first campus deployment in the world, and they choose UST. And now we aim to recruit 300 students to participate in this. And so the students will receive free SIM cards and T-shirts and coffee, but they need to run these applications. So when I getting tired of traveling to very extreme places or exotic places, I also recently also trying to teach to connect people with the machines. So some computer human intelligence, but mainly you building system. So you're trying to build system to teach machine to understand about the emotion of people. So basically use camera or some other patterns, things. So this is some project sponsor, we get a fund from Disney. So one of the project maybe the aim is to help the doors of the Disney company to understand about the emotion of the people, the visitors in the amusement park. So we also build this system for people to interact with the camera to control their privacy, because there are lots of cameras everywhere, right? So if you can have a way to communicate with the camera that I don't want to be in the picture, then you will be removed from the pictures. So this is one example, and we're also building an app actually called V Camera, because we know the Asian people like to always put a V when they take a picture. So we're trying to build this app and put it to Android. So when people put a V, they will be disappear from the picture. So just a drug. And then we also build another system trying to provide some ubiquitous interaction between human and devices by using glow glasses. So basically, you can this is demo, right? You can drag, you can see what you see from the from your glass. They can be connected, so you can move file from one computer to a printer or to a projector, and it worked out quite nicely. So I think I'm almost, yeah.
Where's mine? All right, I'm going to give you a brief introduction to my past and also my current research. So basically, what you see are really my major research areas. The first one is cryptography. I also do research into coding theory sometimes. I also work on interplays between the two areas. And sometimes I also work on mathematical foundations of the two areas. Basically, cryptography deals with security solutions for providing the following security services. The first one is the data confidentiality. The second one is the data integrity. The third one is the non-repudiation. So basically, in cryptography, we use digital signature techniques for providing this service. For data integrity, usually we use authentication codes. For providing this service, for data confidentiality service, we use encryption and decryption solutions. And also, anonymity is another topic within cryptography. And we have also the so-called secret sharing schemes. So personally, I worked on some areas within cryptography. So basically, in the past 20 years, I worked on stream ciphers. So this is a special type of ciphers for encryption and decryption. I also worked on authentication codes and also secret sharing schemes. So I started working on cryptography in the 80s. So basically, I'm a cryptographer by training. So my second research area is coding theory. Coding theory has two parts. The first part is about source coding. So this is how to express information efficiently. And the second part is about channel coding. So we may have data in storage. We may have data in transmission. Errors may occur to our data. The question now is how do we detect errors and also correct errors occur to our data, either in storage or in transmission. Within coding theory, I work only on some sub-areas. Basically, I work on linear codes and also especially cyclic codes. I started working on coding theory about 20 years ago. As I mentioned earlier, sometimes I worked on interplays between the two areas. So this is because coding theory and cryptography, they are closely related to each other. In particular, I worked on some interplays between stream ciphers and also linear codes. I also worked on interactions between authentication codes and also linear codes. Also in the past, I was also interested in some collections between linear codes and also secret sharing schemes. Cryptography and coding theory, these are really my two major research areas. But in both areas, we need mathematical tools. So sometimes I worked on mathematical foundations of these two areas. Because in these two areas, sometimes we need algebra, Sometimes we need number theory, and sometimes we need some tools in combinatorics. Sometimes we need some techniques from the finite geometry, and also sometimes we may employ graph theory. So basically, I'm interested in discrete mathematics in general. This is because discrete mathematics has really a lot of applications in both coding theory and cryptography. So this is what I have.
My question is about the traditional Chinese medicine. The first question is that how do you construct the tree model? Is it construct directly from data, or is it construct by domain experts? And the other question is that is it possible that given the same patient case, different doctors gives different diagnosed results? And some results might be contradictory. So how do you resolve such contradiction? Thank you.
So the first question, the input analysis. The input analysis is just symptom data. So we have my collaborators. They get a lot of grants. Send people to the hospital. Have a survey form. In the form they have like typically around 100 symptoms. They'll go through each symptom and the patient they tick. That's the all information. From that information, then you come to this algorithm. I said, it would take 10 years to develop. So basically, the algorithm will look for co-occurrence of symptoms. They have like 5 symptoms that usually happen in one patient or second patient that will indicate something. So we'll detect those patterns. We'll construct the model. Roughly the idea. For the second question, that's exactly the problem that we try to solve. I mean, if you go to the same patient, if you visit a different doctor, and the diagnosis will be different. That's actually a serious problem. So now what we try to do is we try to collect a lot of information from the patient data, and we do the class analysis. So each cluster of patient will have certain properties. For example, this cluster will have those 5 symptoms. It will, close to something. Okay, then for new patient come along, we'll
education belongs to this cluster. So by that way, we give a cluster label, and that will be kind of more objective or independent of the.
I say today's speaker, they cover 5 different areas, to almost cover all areas in our department. So question for other speakers, I can ask one because I mean, let's talk is social dating, human computer. Can't we also connecting human and computer? One question our computer science is really good at understand the data, understand the computer. But how do you understand the people? Any fancy systematic way to understand the people habits? Basically, for example, one of the study that I mentioned about the trip that we went to Sweden, right, the north, very north. So it's ago. So there, the reindeer herder, they're doing reindeer herding. You don't know. So in the winter, it's very cold. It's minus 30 degrees, right? People move to the city, but in the summer, they move the reindeer into this very remote area and do the herding. So we are proposing to give them some kind of application, data application that they want. Then we have to, at the beginning, we didn't know what they really like to see, right? So you need to ask the people, so what kind of application that you expect? And so they told many people answer the question, but that kind of application that you would not expect. They told us that we would like to know about, we would like to read newspaper. Even the newspaper was like 3 or 4 days old. We don't care, but we just want to keep touch with the people outside there. We want to know what's happening there. So I think it's very important to understand about the users, what they really need before you really design a system. Maybe people think, oh, okay, these people there, they make let's get them to it's not really what get in touch with. Then you can, if they can tolerate 3 or 4 days delay, then it's okay because area is covered most of the helicopters usually go there, twice a week. So yeah.
Using questionnaires, interviews, etc. But the most extreme way, so for example, someone's tried to study the use of technology in Disneyland. He actually get a job in Disneyland. So he worked there for half a year and observe and shadowing people, chat with colleagues and also customers to get data. So that's one extreme way to get real understanding of people's needs and taste. Another is you can also infer things from data, just using more qualitative, more computational method. For example, I'm working on Damu, so I crawl a lot of Damu data and analyze the content to actually understand what people want to get from that social media or social network. So there are both ways, and you can definitely combine both. So first about emotion words, we are dealing with emotion words in 2 ways. One way is they actually are signals of some sentiments. So people are positive or negative about certain things. So then we will use it to tag the content. So what they are talking about and their sentiment towards that particular topic. And another occasion is people just laughing. They just show that, oh, this is funny. So a lot of 2333, things like that. It's just people showing that they're engaged. So that we use it to show the arousal and engagement of the audience and use it as another dimension. And about the linguistic analysis, we look into both the semantic meanings, like what do people really mean there, and also the syntactic meanings, people's language patterns. For example, we notice that people often omit pronouns. They don't mention I, you, he, she in their conversations, and why that happens, we do analysis on that. So we look into both.
Okay, so any questions on the software engineering, fix bugs, build a data center, and something like that? Okay, okay.
So Professor Chen Kai, so can you give us how powerful your cluster is, and then what requirements people do need if you want to use your cluster, like what kind of language you want to learn?
So how powerful it is? Okay. So basically, we can it can be very powerful, depending on how powerful you want, and because it's scalable, the system can be dynamic, grow if you need more power to solve your problem. And I think there are a lot regarding what kind of language. I think it depends on what kind of project you are doing. For example, those big data analysis, or you are dealing with a very large data set, you may use Hadoop, Spark, or various distributed learning algorithms. And actually, you don't need to know very detailed about these languages. You just know how to call the functions. It's how to do the, you use the API. That, yeah.
Okay, so questions from students? Okay, yeah, student.
So what is which task may become more difficult? For example, is there any research on recognizing Chinese language or other maybe Japanese, and whether it's more important, whether it's more difficult than recognize English speech? Thank you.
Just in general, it turns out no matter what language you can sit there. No matter what language you are doing the recognition on, the technology is the same. So far, it's phonetic. So assuming all language are phonetic, of course. If your language doesn't have sound, and there's difference. If we're talking speech recognition, right? So it turns out even Chinese, we do use the same technology to do it. Yeah, so it turns out it works equally well. In terms of dialect is a problem. So now that two questions now. So whether you really want to identify the dialect, or in general we don't care. So for example, I created this English recognition system. Say Google built this system, right? So it doesn't matter where you are from. You are from Hong Kong, China, or from America. They want that if the same recognizer can recognize your voice. So even you don't speak, we may not speak with exactly the American accent, right? So the difficulty of building such system is even you speak with different accent, I still can recognize it. That's one way. The other way, of course, you can build an accent-dependent recognizer. So this recognizer only works for American English. Then another recognizer works on British English. Another one works on Hong Kong English, for example. You can do that too. But that's also doable. But usually they say if there's only one recognizer, that anyone can use it, of course, then it's easier for them to build. So in terms of different language, some language have some just inherent, it's more difficult because they have sounds that are easily confusable. Like in English, even for us, I guess most of us still have a hard time unless Andrew Horner, H-M-A-N and M-E-N. If you ask everyone here to say M-A-N and M-E-N, most of us cannot really tell the difference, right? So just that some sounds in a language is just inherently more difficult to recognize. And so different pair of sound may have different discriminability between those two sounds. Some are more easily to distinguish, but some are most easily to confuse. But other than that, the technology is basically the same.
Okay. Yeah, this student.
What's new in neural network?
Yeah, about DNN.
Yeah.
I mean, what's the novelty of solving your problem with DNN structure, and why this structure is a good structure for your problem for speech recognition?
Yeah, thank you. Yeah, this is a question many people want to know. So DNN, we have done it 30 years ago using neural network, and now it's deeper, just basically really just deeper. So in a sense, what happened is DNN turns out to be very good for many tasks, not just on speech, in image recognition. So usually it's used as a way to build a mathematical model for distribution. So in general, you can say that GMM, if given enough data, the hard part is you never know the model. You never know really what model represents a particular problem. Whether it's, and GMM usually is to say, given enough data, you can just increase the number of mixture components, then you can fit any data you want. But just in theory, if you have infinite number of data, then now the next question is, will there be any model more efficient to, given the same set of data, which model is more efficient to model them? So it's turned out the deep neural network now is a very efficient way to learn a lot of nonlinearity, better than the GMM in general. And it's proven in many tasks that they can do it. And one reason for its resurgence is now you know how to train it. So before, back in 30 years ago, everyone have been using this multi-layer perceptron. People have tried to use 2 layers, 3 layers. No one has successfully. And of course, one problem at that time is the computation power. You don't have such computational power to learn a big neural network. But just recent research showed that a shallow network with a lot of hidden unit is not as good as a deep network with fewer units on each hidden layer. So that is, so you use many nonlinearity to model your distribution. It turns out it's more efficient than before. Thanks for the question.
Yeah, I think time is up, and we have a refreshment outside, and it provides some informal setting. Then you can still ask questions about the speakers. So let's, thank all the speakers again.